itself to be a integral, right? Okay, so how to solve this one? So this one should be how to solve this one? You can either just implement your standard formula, it's a minus b plus minus root square of b square minus 0.c divided by 3. Another way is you can see this 0.2 can be 0.5 multiplied with 0.4 and 0.5 plus 0.4. Right? So up to you. And either just want to solve this one, minus b with 0.9 plus b square minus 4ac divided by 0. So this one will be 0.9 plus 0.01. Right? So will be 0.9 plus 0.1. Okay. 5. So this is one way. The other way you can this one will be another way you can solve this one. So you can also solve your z as 0.1, 0.5. So now what is the root of this z function? 0.1, 0.5, right? So it's a system stable now. So the system should be stable, right? Because both roots are within your unit circle, right? The quantity is less than 1. So if you want to try, you can also use the Excel to plot the data. Then this is something. So this is something I can get directly from the difference equation. But if you only look at the stability, as long as you find the root, should be okay already. But if you want to determine what is the general solution, what is the general function of this difference equation, expression, okay. So how can you do? You have to do further. You have to know what is the initial condition, right? You have to know what the initial condition. You need to know how to solve the particular difference equation. Alright? In this case, if you know the initial condition, okay, last week, when we discussed about the PID, last week when we talked about how to approximate the differential equation by difference equation, right? Okay, so last week when we talked about the differential equation approximation as a difference equation, we had basically talked about the Euler's over backward and so forth, right? So similarly for the integration, they also have similar rules, okay, but we discuss them as forward rectangular, backward rectangular, and they can also take something in between that we call the triangle. So there are 3 ways to approximate the integration. Okay, so if let's say we take your output function as the integration of the input, okay, your in is your input. If you use the so-called forward rectangular, it means you are going to take the current function and you forward. So it means your output will be your current input multiplied with the time with your current input. So this is the forward rectangular. You can also look at the backward rectangular. It means we are going to take the current input backward to form the rectangular. Then this is your output. Or you can also take the trapezoidal, so means you take the average between your current and the previous one. Okay, you bring this one as the trapezoidal, then you take the average. So what we mean is, if we have a function, this is my EP. If my UP is integration of EP towards the time, so means ideally it should be the area, right? Cover under the curve, accumulated all the time. And this is something you have learned in very detail. So now what we want to do is now we only have a digital information. Right? First of all, because my data is digital, so I digitize, so I digitize, so I digitize, so I digitize, so I digitize. So instead of continuous data in the digital domain, my signal is only digital signal, right? So now I give everybody a good picture. Your digital signal is discrete, right? So we have discrete data according to the sampling time. So once we get the discrete one, if we want to do integration, how we are going to do? Instead of integration, we are going to do summation. So how we do the summation? We still want to integrate. Integrate with what? Integrate with time. So each sampling time we accumulate certain number for us. So basically the integration in the digital domain will be the summation of all the time blocks. Okay, of all the time blocks. So if we are going to apply the backward rectangular, it means when my time is here, my integration will look from my previous time to here. If previous one is 0, this one is 0. Then when I come to the time 2, I take the previous. When I come to time 3, I take the previous. When I come to time 4, I take the previous. When I come to time 5, I come to the nearest. When I come to 6, I get the time 4. Okay, so this one, this one, this one, this one, this one, this one, we sum up. Will be my integration, will be my UP. Because my UP is an integration of my EP, right? So if we implement the so-called back forward, so the forward rectangular, so we are bring the previous one forward to the last. If we adopt the so-called backward rectangular, it's still rectangular. So when I'm at time 1, I'm going to backward my signal to the previous one. So I'm going to take this one. When I'm at the time 2, I'm going to take this one backward. When I'm at time 3, I take this one backward. When I'm time 4, I take this one backward. When I'm time 5, I take this one backward. When I'm time 6, and okay. And similarly for the trapezoidal is to link this one, 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 link this one as a trapezoidal. Okay. Then we sum up all the area covered. Okay. And this one in math is also called the Riemann sum. Okay, because the Riemann is one of the expectations. Okay, proposed this way to do the integration. And once your time difference, your time interval limit to 0, then your summation will become integration. Okay? So basically when you learn your maths, I do hope the professor has shared with you. Differentiation actually is a limit in the approximation of the difference when your time interval limit to 0. Your integration basically is a summation when your time interval limit to 0. So when your time difference limit to 0, or no matter whether you're using forward, backward, or the trapezoidal, it should converge to the same function. And the one should be your integration. Because once you are able to cut the time interval to be as small as possible, eventually you are able to get so-called the integration. Okay, so integration is just a continuous summation when your time interval limit. Okay, so now because the definition of the integration is basically the summation of the integrations. So up to today, I do hope you have an overview picture about what the relationship between the differential equation and difference equation, the integration and the summation, or sometimes we call the combination. As I mentioned, in your continuous domain, when you want to solve the differential equation, you can solve the differential equation by the general, simultaneous, and particular differential equation solution, right? You can also adopt the Laplace transform. Similarly, in the differential domain, you can solve the difference equation by a general form, then you have a particular way to solve, then you solve the difference equation to get your function of k. Alternatively, you can also have another type of approach, which is to the transform. So in your continuous domain, you can do the Laplace transform to transform your time domain to S domain. Similarly, in the digital domain, you can transform your time difference equation into a Z function. And this is your Z transform. I have also put up some of the extra articles which you can easily get from online to see the relationship between the Laplace transform and the Z transform. Okay? So just now we are talking about the integration. We can approximate the integration as a summation. Now let's do something to practice. To do the Z transform of the trapezoidal. Okay? To do the Z transform of the trapezoidal integration. So the trapezoidal basically taking the average of your current input and your previous input, right? Your half is the average. You multiply with the time. Multiply with the time interval. And because it's so-called the integration, so you are going to accumulate it. So you accumulate it by your previous. So for this one, how do you want to do the Z transform? Z transform actually you see the formula is also very similar to the Laplace transform. It just instead of e power of SE, you have e power, you have a Z power of k. That's all. So you are going to do this one. You pick every input or every output, multiply with the function with Z power minus k. Then you do the summation from most negative to the most positive. Negative infinite to the positive infinite, you get your uk in the Z transform. Similarly, you can do this for your k minus 1 and your ek and your ek minus 1. So after you obtain this, you can do a simple mathematic conversion. Because you notice, this one is uk minus 1. Here is your uk. So I want to convert this one in the same format as uk. So how can I do? I assume another variable which is j. I assume j equal to k minus 1. Okay? Here I assume I take j as k minus 1, which is a very simple mathematical substitution. So if I take j as k minus 1, so this one becomes sigma summation j here from most negative to the most positive. I have uj z power minus j, because now your k becomes j plus 1, right? So clearly j plus 1. Is that right? And I want to be standardized. Uj is there, uj, so here I want to see minus j. So if I see minus j, what I have? I have j power minus 1. And this one, I can, because this one has nothing to do with j.
Okay, in this summation is related with J. This one your Z power minus 1 have nothing to do with J, so I can shift this one out. So now I come out this one. So this one is what? This one is just the definition of the Z transform. Right? It's the same thing. So this one is basically a function of your U Z. But now you see there's something in front. And this is a critical part. Why we have a Z power minus 1? Because we are doing the Z transform of 1. We are doing the Z transform as a function of K minus 1. K minus 1 is what? What's the difference between K and K minus 1? Minus 1. That 1 minus 1 is what? Means one step in advance. One step in 4. Correct, right? Alternative means one time delay. Your UK minus 1, if you put one time delay, it becomes UK. When you delay this one to the moment, your UK minus 1 is a one time delay of the data in the previous cycle. You see, the one time delay or one time shift in delay, eventually it just becomes a multiplication of Z power minus 1 into your Z function. Correspondingly, you can do similar exercise. If you have a second order, if you have a K minus 2, then what do you get? You will get Z power minus 2. If you got 3 times delay, what do you get? You get Z power minus 3. If you still remember your Laplace transform, what the S operator means? Your S operator means one time differentiation. If you got 2 time differentiation, what do you get? You get S squared. If you got 3 time differentiation, what do you get? You get S power 3, S to B, right? So similarly, in the difference equation, in difference equation we don't have differentiation, we don't have integration, but what we have? We got the difference. Difference was what? With what? Difference with your time delay. Difference between your K and K minus 1 and K minus 2 and K minus 3. So in the digital domain, in the discrete function, your time delay, your function of K minus 1, minus 2 or minus n, after you have done the Z transform, you will result in Z power minus n. So you have one time delay, you get minus 1, you get 2 time delay, you get power minus 2. You get n times the delay, you get minus Z power minus n. And you can also move forward. If you have right hand shift, which if let me say you need to estimate what is the future, then it will be Z power plus 1, Z power plus 2, plus 3. Then your K plus 1 plus 2 plus n will be converted into Z power plus n. Okay? So you can also do similar things for your input. Then you will get your input EK will be converted to EZ. EK minus 1 will be Z power minus 1 multiplied with EZ. So now if you similarly as your Laplace transform, you do the input output, what you did? You put your output S function divided by input function, right? So it's something called your transfer function in your continuous domain. But now you also have certain function with your output, your certain function of input. You ship all your output here, you ship all your input here, so what you can get? You can also get the transfer function between your output and input in a function as a function of Z. Is that right? So this will be also called the Z operator or the Z function of your trapezoidal. So So you can see actually what we are doing in the digital control is something quite similar. But you kind of have to simplify it. Okay? Any questions? So now you see the z power minus 1 works as a time shift or delay. Okay? And it's a back shift of a center by z power minus 1. Of course, if you have a forward shift, okay, maybe z power cos b. So if you have 2 time shift, then your order becomes 2. If you have 3 time shift, becomes 3. And if you want, we can do similar things. Just now we talk about integration, right? Then how about the differentiation? We also do similar things. If we also want to find out differentiation, you can do similar things. And you will notice a certain relationship between the S operator and your Z operator. And this is something we are going to learn further in a 2 weeks time, and this is something called the Plastics method. Okay, for the digital approximation about integration. Okay, and sometimes you also call the linear transformation. If you want, we can also try practice about the forward and backward. Okay, you will also get some approximation between your S operator and your Z operator. Okay, bear in mind, if you are adopting different differential manner or method, the correlationship between your S operator and your Z operator will be different. In the same case, these three are different. Okay? And we are going to address this one further in about 2 weeks' time. Okay, maybe we have 5 minutes break. Okay, we will come back maybe around 10:20. Okay, so now we are going to continue about the